Hi, I'm Wim Bogaerts from Ghent University and IMEC, and I represent the MORPHIC project, in which of the past 4 years we've been building programmable silicon photonic circuits enabled by MEMS devices. Now you can ask yourself, when we think about programmable photonic circuits or programmable circuits, we don't really think about photonics, we think about electronics. And indeed, over the past decades, we've seen a dramatic evolution of electronic capabilities, including general-purpose programmable ICs that can be bought off the shelf and reconfigured to do many different things. The most prominent example of that is a field programmable gate array, or an FPGA. Now, in photonics, we've seen a similar evolution in terms of integration density, where silicon photonics now boasts 10,000 or 100,000 of building blocks on the same chip. However, most of the silicon photonic circuits today are application specific and not general purpose programmable photonic chips. Now, why does this matter? Why is this important, this programmability? Well, if you think about the time it takes to develop a new product based on a photonic chip, a lot of time goes into the design, manufacturing, and testing of your photonic chip, which can easily take you more than a year and $500,000 to $1 million. Now compare that with prototyping something new in electronics. You don't need it to make a new chip. You buy an off-the-shelf programmable electronics chip and you start programming and developing until you get something that works. So photonics has an excessively long time for development for new chip products. So that's an enormous entry barrier for new innovators and new product developers. What if you would have a programmable photonic chip? Well, in that case, you would need a chip that looks a bit like this, where you have optical inputs and you can route your light on your optical chip based on electronically configurable tunable elements. So you can switch your light to a different output, for instance, or you can do splitting of your light and even wavelength filtering by programming interferometers or resonators. If you combine this programmable routing of light with high-speed modulation, high-speed detection, amplifiers, and other functional blocks, you get a general-purpose programmable photonic chip. And that gives you an enormous benefit in terms of development capabilities, because now you can lower your development costs based on off-the-shelf chips, which gives you much shorter time to market. On top of that, your devices become upgradable because they're software defined. And this is something that we currently expect from electronics products, that you can get over-the-air upgrades or firmware upgrades. And maybe the biggest benefit of having something like a programmable photonics platform would be that you suddenly address a whole different community of electronic and photonic and programming and computer engineers that up till now could not access this light-based technology. And that's a much larger community than that of photonic engineers. Now, what do you need to build this kind of chip? Well, at the core of such a waveguide mesh is a component or a circuit that we call an optical gate, a 2x2 optical gate. It essentially has two input waveguides and two output waveguides, and inside the component you can mix your light from your two waveguides together with an arbitrary coupling ratio, and you can also control the relative phase delay. Now, the building blocks you need to implement this on a chip are an optical phase shifter and a tunable coupler, which is essentially a tunable beam splitter. Now, if you have these two components, you can start building circuits. And one of the first circuits that really tried to implement such a general purpose waveguide mesh was this example from the Politecnica de Valencia, where they basically built a 7-cell hexagonal mesh that could already, with the 60 tunable elements, 30 tunable couplers or 30 optical gates, it could already do more than 100 different circuits. And just to illustrate this, if you take this circuit, by switching your couplers from bar to cross, you can basically route your light anywhere on the circuit from any port to any other port, and even route multiple paths of light through the same port. You can configure it as a splitter. And if you can do it as a splitter, you can also use it as a combiner, which allows you now to build an interferometer. And if you add a delay line to your interferometer, you get a filter. You get a wavelength dependent response. And likewise, you can route your light in a loop to make a ring resonator, which gives you also a wavelength dependent response. And together this allows you to make arbitrary filters. Now, well, maybe not arbitrary, because the quality of your filter and the free spectral range depends very much on the properties of these optical gates, of these tunable couplers. So if you want a large free spectral range, you need a tunable coupler, you need an optical gate with a very short optical length. If you want high quality factors, you need low losses. So there's a big drive to make better tunable couplers that are shorter, more compact. Also, these tunable couplers, you don't need one or two of them, you need tens or hundreds or even thousands of them. So there's a scaling issue here. If we really want to make large-scale circuits, we need good tunable couplers, good phase shifters that are compact, have a short optical length, low optical loss, and consume very little power. And you can make lots of them and they all work. Now, this is what we set out to do in MORPHIC. And as a starting point, we started from IMEC's ICIP50G Silicon Photonics platform, which is a fully functional platform with modulators and detectors operating at 50 gigabit per second. Now, the standard phase shifter and actuator in this platform is a heater. And this is very simple. You take a metal resistor or a silicon resistor and you put it close to your waveguide and you run power through it and you get a phase shift. And indeed, in the platform, we have both kinds of heaters. We have top heaters with metal or doped silicon heaters. However, there's a little catch. Well, it's actually a big catch because these heaters, they run quite hot. So you get this very high power consumption of your heaters. Essentially, you're just burning power. And so we're looking for alternatives inside this platform. The carrier-based modulators can act as a phase shifter, but they're not really very suitable because they're long and they're lossy. So the solution that we started developing was this mechanical approach where we incorporated MEMS devices inside the Silicon Photonics platform. Now that idea is not entirely new. Over the past 15 years, people have been developing different types of waveguide MEMS-based devices in Silicon Photonics because it's a very strong effect. You're moving silicon. It's electrostatically actuated, so low electrical power. And in principle, with mechanical latching, you can make it non-volatile. And the concept is actually very straightforward. You take two waveguides, and if you move them apart, you change the coupling between the waveguides. And tada, you get a tunable coupler. Whether you do the actuation horizontally or vertically, that doesn't really matter much. You can even do it vertically between two waveguides that are in different layers. And to turn this into a phase shifter is actually fairly straightforward. You just replace one of the two waveguides with a thinner beam of silicon that acts as a perturbation to your waveguide mode. And so that is what MORPHIC, with the 6 partners that I list here, is doing, is to take this Silicon Photonics platform and enable it with MEMS. Now to do that, you need to solve one problem. Basically, you need to make the waveguides here freestanding, but as you see, they're buried inside a stack of dielectric. So the first thing we need to do is open up this stack, which is luckily a process that's already available inside IMEC's technology portfolio to make silicon photonic sensors. And now the second step is to add an alumina layer to protect all the parts of the silicon chip which we don't want to touch, which need to remain pristine, so that we can open up the area where we want the freestanding waveguides with a very aggressive vapor HF etch, which selectively remove the buried oxide underneath the silicon. And what you get are these very wonderful SEM pictures where you see the freestanding rib waveguides here, and then they transition into these freestanding wires that are suspended in a couple of places. Now, one thing that you might notice here is this little ski on the side, which is a part of a phase shifter, like one of these thin beams of silicon next to the waveguide. And if we take a closer look at one of these phase shifters, we see that the waveguide is at the top, so your light goes from left to right through your device. And next to the waveguide is this thinner beam of silicon, which is suspended onto these folded springs here, which can then move on this shuttle by actuating the comb drive at the bottom. And if you put this whole device into an electrical, mechanical, and optical simulator, you find a response curve that looks a bit like this, which gives you, for an actuation of 30 volts, a pi phase shift. Now, the experiment gives us even a somewhat better result, because there's always a bit of a difference in the mechanical properties of the layers compared to what you model, and we see that we already get a pi phase shift for 20 volts. And this can be further optimized by playing with the width and spacing of your waveguide and your beam. So for instance, we see if we make the waveguide narrower, that we can get a much stronger response, but this also comes at the cost of a higher insertion loss. Now, if we put not just a DC signal on these MEMS devices, but we also look at their response time, we see that indeed, this is a spring-based system, we see that it has a resonance frequency around 500 kilohertz, which gives us basically a good response time of, let's say, 5 to 10 microseconds for switching such MEMS devices. Now, this is a phase shifter. We can apply the same principles to a tunable coupler. So the first thing, of course, you need is a good directional coupler. So we designed a directional coupler. It's difficult to see here, but that has a slightly tapered profile, so to give it a broadband response. And then by pulling this directional coupler apart, we can move it from cross state to bar state to cross state again. So basically, you take that coupler, you attach it to a movable structure like a comb drive, and now you can basically tune your light from cross state to bar state by just pulling the coupler apart. And this is the device that we get here. Now, a similar the same device you can also make with a vertical actuation. For instance, in this particular case, so you have your light coming in here. Now it goes through two of these couplers, and by electrostatic force between your device layer and the substrate, you can now pull this device down towards the substrate, and basically switching the coupling from cross state to bar state. Again, the same device here actuated, and we see that for this particular device, we get indeed a very good switching behavior between of roughly minus 15 dB extinction ratio. You can even use these MEMS to make much more compact switches. For instance, this is an example of a 1x2 switch, where you have your waveguide coming in at the top and two output waveguides at the bottom. And you can now move this little shuttle in the middle by just pulling it to either electrode 1 or electrode 2. Now this takes a bit of careful design, because you have to design both the electrical, mechanical, and optical properties. You need good coupling between these two tips optically, but you also need to make sure that your response to your electrostatic actuation is as linear as possible, which requires a careful shaping of your electrodes. Now, what we get is something like this, where depending on whether we pull on the red or the blue electrode, we can switch all the light to either one or the other side with 25 dB extinction ratio. And that's a very, very compact switch, which can very easily be actuated. Now, there's a catch with all these MEMS devices. So if you have your light in here, you see that the MEMS devices are exposed to air. Does that make them really fragile? Well, we know from MEMS sensors that MEMS devices can be quite robust. So on their own, there's not really a danger. The problem is that, of course, if there's a little speck of dirt falling on this MEMS device, we have a problem. And so in the MORPHIC project, we address this by adding silicon lids onto the MEMS cavities. And we do that in a very local way. So we use the metal layer of the silicon photonics, basically these metal rings, we use them as a bonding layer for thermocompression bonding, where we do locally silicon photonics caps, silicon caps onto the cavities. And this is done on a wafer scale process. So this is a wafer bonding process. And indeed, we can see one of these devices here. So you see two of these silicon photonic MEMS devices inside one of these rectangular sealing rings, which are implemented in the top metal layer of the silicon photonics. And then next to that, we see these these silicon lids. And here you can see it as well, the silicon lids, and you also see the metal bond pads in between the lids, and also the areas where we have grating couplers. Now, this wafer scale sealing is quite powerful because it's a wafer scale process. You process all the lids in one go, and then you transfer them onto your silicon photonics. And the sealing yield is quite high. So we're seeing like a sealing yield of over 95% over a long time. And this we can measure by measuring the deflection of these individual lids, because this sealing happens in vacuum. Also, we test the MEMS devices after the sealing, and for instance, here you see one of these interferometers. You see that you do get a clear interferometer pattern, which means that the MEMS devices are optically enabled. They haven't collapsed. The vacuum also gives you some advantages, because by removing the air from around the MEMS devices, you also decrease the damping, which means that the MEMS devices are faster. And indeed, you see that the resonance frequency is higher and much sharper than when you have the device without the sealing protection. We also tested these devices in stress tests. So we basically did vibration and temperature cycling at 5G temperatures between -40 and 85 degrees with multiple cycles, and we see that the MEMS devices and the sealing seems to survive without much of a problem. Now that gives us a toolbox of waveguides and grating couplers and high-speed modulators and detectors that we already have in the ICIP50G platform, and augmented with low-power switches, tunable couplers, and phase shifters to build programmable photonics like these hexagonal waveguide meshes. And that's exactly what we've been doing. So you have this example here of a unit cell of such a hexagonal waveguide mesh, and it doesn't really look hexagonal because we rotated the elements in such a way that it's easier to stack them. But you see that the elements here have 3 tunable couplers and 3 phase shifters in each unit cell. Now, a unit cell is fairly small, but you have to combine many of those together on the same chip. So you see this massive chip of 22 by 22 millimeters, where you can put lots of devices and circuits. And so if you really want to scale circuits to large number of actuators, you need a way to address all the elements on that chip in a way that still allows you to put many components close together. And so with a chip with this type of density, you need thousands of electrical interfaces. So we came up with a solution that relies on a standard layout of these unit cells, where you have a fixed pitch of 150 microns between each electrical bond pad, and you can do up to 3,300 of these DC connections on the grid. Now, these are closely packed together, so you need some way to fan this out. You don't need to use all of these 3,300 connections. You can put your circuits there and use the ones that you want, but still, how are you going to get all of these to the outside world? And for that, in the MORPHIC project, Tyndall has been developing this large-scale interposer. It's a ceramic interposer with 21 layers, so it's a really large-scale fan-out circuit, and it allows you to basically connect all 3,300 DC connections to the outside world. On top of that, if you look at this interposer here zoomed in, you see that it not only has this regular grid for these 3,300 connections, but it also has interfaces for the high-speed connections, including 3 footprints for multi-TIAs, transimpedance amplifiers. So if you look at the individual building blocks here, you see these 90 micron wide pads. Now, on the back side of this interposer, we of course have a much wider grid where all the connections have been routed to the footprints of spring connectors 200 pin connectors. So you have 16 of these in a grid, and then another extra grid connector which handles the RF frequency connectors and some auxiliary connections. Now once you have that, you now need to bring everything together. So we do a gold stud bumping on the silicon chip, we do solder jetting on the interposer. The silicon chip is flip chipped onto the interposer, which is not trivial with this large number of connections. There's an underfill of epoxy, and then we're at the stage where we now have to package this into a larger assembly. One of the nice things is that you can take an X-ray of this assembly and look at whether everything is properly aligned, and you do see indeed that the flip chip contacts and the interposer contacts are just enough aligned, but you also see, interesting, these deep interposer vias or the contours of the sealing lids and the sealing rings. Now the next step, which is currently ongoing, is to take this interposer with these silicon photonic chips and do a fiber array attachment, and then mount it onto a printed circuit board, either using the spring connectors or low temperature solder balls. And these circuit boards can become quite large because you basically route all the connections that you want from the chip, you route it to the outside world. So we've chosen for a flexible solution using 40-pin flex connectors. So depending on the number of interfaces, we add multiple, more or less of these connectors, which can then be connected to custom developed driver boards that we built for these MEMS devices. So we currently have driver boards that can handle up to 64 channels at 60 volts with a 14-bit precision, and at the same time also read out 32 photodetector channels. And everything is programmable. It's controlled by a BeagleBone mini PC. So these driver electronics, they can handle high voltage. It also allows you, because we combine the readouts and the drivers onto the same board, allows you to do feedback control, either on the microcontroller or in the software framework that we've built around this. So we've built a software framework that allows you to define your programmable photonic mesh. From that, it interfaces to the layout that's actually on the chip, to circuit simulation where you can monitor or model the behavior of your circuit, and to the hardware control, which actually drives the silicon photonic chips itself. And algorithms that we've incorporated in the software framework are, for instance, programming algorithms based on graphs, where we can use graph algorithms to route the light through the mesh. For instance, using this multi-input to multi-output routing, including congestion avoidance. So it's a multi-level optimization problem. We also have splitter algorithms and filter algorithms. Now, this basically shows that your programmable photonic chip is more than just a chip. It's a photonics device plus electronics plus packaging plus software. So there's an entire technology stack that comes with this concept of programmable photonics, not just a photonic chip. And that's exactly what we've been trying to build in MORPHIC, and which is currently in progress. So we've already filled multiple of these blocks into this technology stack, where we're really building a silicon photonics platform, starting from the MEMS devices all the way up to the larger circuits and the packaging technology, with the whole idea of building a flexible general purpose photonic chip that can be used for multiple applications and basically fulfill the role of programmable electronics, but then for applications of light. And with that, I want to conclude, and I would very much like to thank the entire MORPHIC team that has contributed to all the results that I've shown here. Thank you.